Welcome to another probability distributions video. We continue talking about normal distribution. Straight into example 1. The birth weights of baby girls at Wellington Hospital have been recorded and appear to be normally distributed with a mean mass of 2.6 kilograms and a standard deviation of 0.3 kilograms. We're going to work out what proportion of baby girls at Wellington Hospital will have a mass less than 3 kilograms. Alright, so our mean is 2.6, standard deviation of 0.3. Let's set up our normal distribution curve, and we want the proportion of babies that are less than 3 kilograms. Alright, so into our calculator, into statistics, distribution, normal distribution, and we select normal cumulative distribution, and we enter our variables. Our lower boundary, I like to put a value way off to the left, like negative 10,000. I know we can't get negative weights. My upper boundary, I'm going to put 3 because we want everything less than 3. Our standard deviation sigma is 0.3. Our mean is 2.6. And then we solve it and execute it to get a probability of 0.9088. So let's round it to 0.9088 to 4 significant figures, or change it into 90.88%. So 90.88% of babies are going to have a mass less than 3 kilograms. Now that's great, fantastic, that works perfectly. It uses continuous data that's being measured, and that's how the normal distribution curve is set up. But let's show you example 2, where we have a small problem. The English test scores for a Year 9 cohort are discrete values and are normally distributed with a mean score of 65.2 and a standard deviation of 13.5. What proportion of test scores are under 50? So we have a mean of 65.2, a standard deviation of 13.5, and we want to know what proportion of the tests are 50 and less. So again, if we go through the process of our calculator and enter in our data, the lower boundary, I'm going to put negative 10,000 once again. My upper, I'm going to put 50 because we want everything 50 and less. My standard deviation is 13.5, and my mean mu is 65.2. Then I solve it and I get a probability of 0.1301, which is about 13%. But there's a small problem here. We've used discrete data. The teacher's basically gone and given ticks along the way and then counted up how many ticks to say this student got 58, this student got 92, and so on. And this normal distribution is not set up for discrete data. So when we use discrete data or rounded data for normal distribution calculations, we need to use what's called continuity corrections to try and be more accurate with our result. Let me try and explain what's going on. Say we want to work out the probability between 7 and 10, and the data's been either discrete data or been rounded. The problem when I say probability of x is greater than 7, we need to adjust that to actually say the lower boundary, the probability has got to be bigger than 6.5. Because if the data was 6.7, it would have been rounded up to 7. So there's a little bit of data sitting in here that we're not using. So we've got to be accurate and reduce our lower boundary down to 6.5. Now the same applies for the upper boundary. The probability of x has been less than 10. Well, again, we need to adjust that boundary and say, actually, we want the probability of x being less than 10.5, because any value like 10.2 will get rounded back down to 10. So we need to change our boundaries. These are called continuity corrections to adjust for discrete data or rounded data when we do normal distribution calculations. So coming back to our test, instead of putting an upper boundary of 50, we're going to adjust it and go up to 50.5, because remember 50.1 will get rounded down to 50 and so on. So we'll adjust our upper boundary up to 50 and we'll go and redo our calculation, and instead of getting 13%, this time we get a probability of 0.1381 or 13.81%, which is a tiny bit more accurate for our calculations. All right, thanks so much for watching.